Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new topic regarding Euler model law, Weber model law, and Mach model law. So in our last few lectures, we are discussing regarding this model laws, different kind of model laws. Like we have already discussed about the Reynolds model law and Faraday model law. So in this lecture, we'll discuss about this three different model laws. Anyway, I'll just give a hint about what we have discussed in our last few lectures. So we have discussed regarding different kind of forces which are affecting the fluid flows. The forces which are affecting the fluid flows. So what are the forces are there? Like inertia force is there, and similarly viscous force, and similarly we have gravity force is there, and pressure force is there, and surface tension force, and we have tensile force is there, or elastic force actually that is elastic force. So these are some forces which are which are affecting in the fluid flows when the fluid is moving condition. So these are forces are affecting on that. So these forces are actually affecting, or from these forces we are able to find out the dimensionless numbers. So dimensionless numbers also we have discussed in our few lectures. What are the dimensionless numbers are there? Suppose like Reynolds number is there, then Faraday number is there, then Euler number, and similarly Weber number and Mach number is there. So these are some dimensionless numbers which is associated with these forces, or which is derived from these forces. Now, though we have seen some difficulties are there to match this all these numbers to the model in the prototype, so that model laws was identified, or it was started. So anyway, so in the last lecture we have completed this Reynolds model law and Faraday model. Now we'll see first one. We'll see about the Euler model law. Euler's model law. Actually, this model law actually depend or fully dependent on the Euler number only, or this model law is actually designed from the Euler number only. So Euler number is what we know, that we have seen that the Euler number is nothing but it is defined as the ratio of the inertia force to the pressure force. Okay. So in the model law we have seen that Euler number used to defined as the square root of inertia force divided by pressure force. Okay, these two things need to be only considered. Now here, this model law actually it is applicable when pressure forces only is only predominant. So pressure force will be more effectively there in addition to inertia force, and remaining other forces should be negligible, or that should not be present in that particular case. And similarly, for Euler, why this Euler's model law is implemented or started, that means the model and prototype what we are designing, model and prototype what we are designing, the Euler model law or this Euler's law should be equal. So let me write here. So Euler model law for the model, it should be equal to the Euler model for the prototype, Euler number for the prototype. So to satisfy these conditions, again we need to consider some kind of parameters. So what are the parameters need to be considered? As we have seen previously, we require some kind of parameters of fluid parameters, that is velocity. Velocity equal to what? Here I can write velocity Vf. So this is velocity of the fluid for the model. Similarly, if I consider this is Pm, because pressure impact is there, so I need to consider P. So that is pressure of fluid for the model. Similarly, I need to consider some parameter of properties of this fluid like density. So this is density of fluid for the model. Similarly, these are the for model parameters. Similarly, I can consider like Vp and rho p and pp. So these are the of similar parameters for the fluid for prototype. because two things we need to design. One is model, another one is prototype. So the parameters what we are considering here, same parameters need to be considered for the prototype. So as per the definition what we have seen, the ratio between the square root of ratio between the inertia force by pressure force. So this one again we can write actually. Actually after solving this one, we have got some equations, because inertia force we have calculated and we solved there, and we have found that rho a v square. Rho a v square. And similarly, this pressure force is nothing but pressure into area we got there. Then after solving this one, actually we got Euler number E equal to Vm divided by, or V by root over of P by rho. So I can calculate I can write this one. This is actually V by P by root over of P by rho. So for the model I can write Pm and rho m, and here it is Vm. Okay, so similarly I can write for the prototype also, because I need to equalize this equation. Okay, so for this equation again I can write here, this is Vp divided by root over of P by rho P. Okay, now here again we can write, if the fluid is same, so fluid is same means we can consider the density also same. If fluid is same, then we can consider the same for what? Same for the model and prototype. If this is same, then we can write the density can be ignored, or it can be same, and finally we can write this like equation Vm by root over of Pm, and here we can write Vp by root over of Pp. So this is the final equation for the Euler model law. Okay, so this one we can give an equation 2, and here I can give some, this is equation suppose 1 we can consider. So this is for the Euler's model law, and this model law where we can apply, that is one more important thing. So this can be applied actually where only pressure will be predominant, pressure force will be predominant as I told you, and remaining other forces should be negligible or can be ignored that. So similarly we can take a place like closed pipe in which when the water is flowing, it should be flows like a turbulent speed will be there. So turbulence should be there, so that we can ignore the viscous force. First is we can ignore the viscous force, and gravity force and surface tension force also will be absent in that particular position, so that we can consider one example like closed pipe where the turbulence flow will be there, and also that it can be applicable for the when cavitation takes place. Okay, so these are some applications of this Euler's model law. Similarly, we'll discuss about the Weber model law. The next one, this is Weber model law. So how we have derived this Euler's model law? Similar manner we need to just derive this Weber model law. So this also we have discussed previously. So it is the ratio actually, just I'll give a hint, it is denoted by We, and it is the ratio of square root of Fa, that inertia force by surface tension force. So we can write this is inertia force by surface tension force. If you want to see this equation how we got and where it derived, you can see our previous lecture where we have discussed in details. So this is Weber number actually, and this Weber model law actually, this is based on the Weber number only. Okay, what is the which is the ratio of square root of inertia force by surface tension force. So let's highlight this. So this one already you have discussed in your previous lectures. Okay, but this model, when you are considering this model law, that means your Weber number for the prototype, Weber number for the model, it should be equal to the Weber number for the prototype. Okay, so in this derivation also we have calculated, because see, Fi is the inertia force, this is the value, and pressure force, this is the value. Similarly, surface tension force also will be like surface tension into length will be there. So for that case also we have solved this one, and we found there actually we found there actually Weber number equal to V by root over of sigma by rho into L. We got that one actually. So now we need to equalize this equation like this model and the prototype. So again here we can write, suppose I can write this one, this equation I can write. Now again we need to consider, okay, let me write the equation here so that we can understand. Like, see, we need to consider the Weber number for both like model and the prototype. So what I can write here, this is Vm, and this is root over of, what is there, sigma m, and divided by, this is rho m and Lm. This is for the model. Okay, this equation is applicable for the model. Similarly, you can write this is Vp divided by root over of sigma p divided by rho p into Lp. So this is the equation. Let's give this equation number 3. Okay. Now in this equation, what are the parameters are there? Let's check it. Now similar parameters what we have taken here. So here also what we need to consider. Again, we need to consider some parameters as I told you previously, like Vm, okay, velocity of the fluid for the model, and similarly density, length. So that also need to be considered. So this is rho m and Lm, and one more is there, that is sigma m. So this is sigma m, means nothing but surface tensile force for the in the model. Surface tensile force in the model. So this is velocity of fluid in the model for the model, and this is density. Already I have written there. This only I'll write here. This is surface tensile force in model. Okay, and this is length of the surface in model. So these are things what I told you, same thing. Now this is for the model we have to consider. Similarly, we need to consider for the, again, like Vp, okay, rho p and Lp, and this is sigma p. So again, surface tensile force for the prototype we need to consider. So corresponding what we have taken, same value, same things we can write for this one also. Okay, now this is our final equation. Now again we need to see what are the applications of this will be there. Though we got this equation, final equation, now we need to just identify where this can be applied, these conditions will be applied. Now I'll give some example for this, like capillary. We can say, because here if you see the surface tension effect is there, so that we can consider, we need to consider the capillary rise in narrow passages. This is one example. Similarly, I can write that maximum wherever the capillary rise in the narrow pipes, or you can say the capillary waves in the channel, or we can write flow over some wears in the small heads. So this is example, and capillary movement. So maximum actually we need to consider the capillary movement. So let me write another one is capillary movement, because this capillary rise and fall will be happen due to this effect of surface tension we have studied in our previous videos. So the capillary movement of water in soil. So that also one effect will be there. So this is all about the Weber number. Similarly, the last one is there, that is Mach model law. So what I told you is a similar concept also again going to use in this Mach model. That's why I have taken all these three models in the same lecture so that you can easily understand here what is happening. So again, this model law in which we can, that actually this model law is designed based on the Mach number. Okay, this model is designed in the Mach number, and this Mach number, what is the definition of the Mach number? Now it is also again similarly, it is defined as the ratio of, again we need to write, it is that if defined as the ratio of square root of inertia force. Inertia force always will be in the numerator. Okay, to the, we need to consider, that is to the, what is the remaining force is there? Now see, pressure force completed, surface tensile force completed, now elastic force. So this is elastic force, Fe. So this is the ratio. So the force due to elastic compression, will be take a predominant role in this condition. That means where this elastic force will be more that we need to consider for this. Along with the inertia force. Inertia force will be present. Along with that, we need to consider the elastic force also. Like for this dynamic similarity, we need to consider that Mach number for the model and the prototype should be equal or similar should be there. So according to this model law, what we can write, the Mach number for the model should be equal to Mach number for the prototype. Now from this equation actually we have derived this one, and we found there actually let me write here, m equal to, we got this Mach number equal to v by, v always will be there in the top. Okay, this is root over of k by rho. So this is the k is actually elastic stress we have taken. Now here only Mach number, this is, as I told you, this equation, as per this equation again we can write this Vm divided by root over of Km by rho m, and this equal to, again we can write this like Vp and by root over of Kp divided by rho p. So again, what are the parameters we have taken here? We need to write again in the side. So that is velocity of the fluid in the model. So this is velocity, and this is okay, what are the new things? I'll write that one, that is Km. So this is elastic stress for the model. Similarly Kp, what I've written, similarly I can write elastic stress for prototype. Okay, these are the difference, and remaining things, so you can see this is density for the model and density for the prototype, that can be written. Now, so this is our final equation. So this equation, let's give it equation number 4. Okay, now again this law, that Mach model law, again when it is derived also it will have some application in that. Now in the application also we have so it is a Mach number, so it is equal to, like, you know, it will be defined what kind of flow is, like supersonic flow, subsonic flow, to identify that flow types we used to use. So basically this model actually applicable for when the aeroplane or flight or sport flight will be moved, like flies. Okay, so this will be used for the aerodynamics. This will be used for the aerodynamics testing. Again, apart from this also, it will be used for underwater testing. Also, this will be used underwater testing of prototypes, or you can say like torpedoes. Again, some example also again, like flow, like, you know, the flow of aeroplanes. The flow of aeroplanes. Okay, the flow of aeroplanes. That means actually we need to consider the flow of aeroplanes, or we can say the projectiles through air of supersonic speed. Okay, that means the velocity of the sound should be more than the velocity of the fluid or that moving body is there, it should be more than the velocity of the sound. So that we need to consider. So these are some examples. Actually each model law we have some examples out there. Anyway, I hope you understand this concept of this Euler model law, Weber model law, and Mach model law. So similarly, what we have derived for the Reynolds model law and Faraday model law. Only we need to consider these are the like what we have derived previously. What is the ratio or what is the definition? Based on that, we can equalize this. It should be equalized for each model and prototype. The number should be equal. Okay. So I hope you understand. Still, if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you.